So actually, it's my great honor to be here to talk to you some of the work we have been doing. And the title of my presentation today is actually Rateless coding-based cooperative transmission or routing for wireless networks. And in fact, right before the presentation, Dr. Brewer was asking me, "Are you ready?" And I told him no. Actually, so it's a very busy day, and hopefully I can walk you through this set of slides and get some idea of what do we mean by rateless coding, what is a cooperative communication, cooperative routing. Again, my name is Lingjia Liu, and for those of you who can pronounce my name in Chinese, it's relatively easy to pronounce. If you cannot, I mean, if you don't know Chinese, you can think about it's kind of ninja with L. Okay, so it's close to ninja with L. All right, so this work is in collaboration with my former PhD student, Dr. Hao Chen. He's currently working in Samsung Research America, and also my collaborators at Air Force Research Lab, Dr. Matthias, Dr. Medley. Oops. All right, so probably I have to, now actually since the chair already mentioned a little bit about my background, so I thought I will briefly touch about who is this guy, why this guy is standing in front of you. So, I mean, I have been working in the field of telecommunication for more than 15 years, and my academic background, currently I'm a professor, associate professor in Virginia Tech. And you have to know hockey before you come here, right? So the word actually, Dr. Brewer gave a very nice explanation about hockey. And before that, I was actually associate professor in ECS at University of Kansas. It's actually Jayhawk. So I give actually this, I mean, probably not everybody hear about this yet. So when I actually go to interview at University of Kansas, they do ask me, so they ask me, do you like Jayhawk? I mean, how do you like Jayhawk? At that time, my answer is that, what is Jayhawk? And then all of a sudden, the environment freezed. They look at me like, why are you here? Okay, so that's actually, I remember, that's why actually when I get interviewed at Virginia Tech, the first thing is search, what is hockey? Trying to figure out what is hockey. I mean, so that, I mean, for those of you who are actually trying to be academia in future, probably you'd better know university where you're going to, right? All right, before that, I was actually from Texas A&M. I'm an Aggie, and it's again, a very big actually. By the way, actually, University of Kansas is a huge university in terms of basketball. Okay, they like basketball, but I think Virginia Tech and Texas A&M are more like a football university. So here football is almost everything. Before that, I got my bachelor from Shanghai Jiao Tong University. I didn't see too many people from China, so we can say this is the best university in China. Okay. Agree? Yeah, this is one of the best universities in China, and especially in engineering institution. And I'm currently serving various journal editors. I'm also helping a lot of international conference and serving as a TPC and symposiums. We are discussing with Dr. Harpreet on some of the symposiums we are involved. All right, I mean, something making me a little bit special. It seems that I'm not that special, at least in wireless VT, is because I didn't come to academia directly from, let's say, academia. So I do have an industrial background. And after I get my PhD, I spent actually around 4 years in standards, in industry. And the big chunk of my time is working in the Samsung Research America. It's actually in Richardson. It's north of Dallas. Okay, so, and Harpreet was also there, right? I mean, so when I was there, I spent 3.5 years there. When I was there, my main job is doing actually standard delegates. So I'm actually a 3GPP delegates. What does that mean? Have you heard about 3GPP? How many have heard about 3GPP? Raise your hand. Wow. Who didn't hear about 3GPP? Raise your hand. Okay, so 3GPP is an organization actually specify a lot of standards such as GSM, GPRS, and things like that. Okay, LTE of course, LTE advanced, and now we are talking about 5G NR, right? They all come from 3GPP family of standards. And my job as Samsung is actually go to the standards meeting. At that time, when I joined Samsung, it was around 2007, 2008 timeframe, and that's where LTE advanced starts, where LTE work goes down and then LTE advanced standards picks up. So I go there. What my job is that I work in the lab, in the research lab, basically writing patents and working on technology, writing patents, and then I also need to go to the standards meeting, present that technology, present that patent, so that that technology can be pushed into standards. okay, and then become standard IP, so everybody has to pay Samsung or cross-license with Samsung. Does that make sense? You probably know why actually, first of all, why Motorola was why Google bought Motorola, right? I mean, for IP, right? They don't like the product. Not like, they later on sell that to Lenovo, right? They sell the hardware part to Lenovo. So, wireless IP is very, very important. So, of course, it's a very challenging job, right? Why have to adopt Samsung's IP, right? You need to adopt Ericsson, Huawei, and all those major companies are there. So later on, after I joined Samsung, after I go to standards meetings several times, I realized Samsung is kind of mean. Why? Because actually most other companies, they usually have two group of people. So one group of people is stay at home working on technology and write patents. Okay, another group of people is that take that patents, take those technology, go to the standards meeting, present it. Okay, delegates. Those are delegates. However, Samsung pay you one salary, ask you to do two things. Okay, you need to do the work and then go there to present. Well, initially I was feeling I'm mistreated. Okay, but later I realized this is extremely rewarding. Why? Because who knows your technology best? Probably yourself, right? You designed it. So you are very comfortable in terms of fighting against to defend your technology and trying to who's the best person to push that technology into the standards. Of course, yourself. Of course, that's based on the assumption that you need to speak English relatively well. Okay? Okay, so that's actually what I'm doing in Samsung. So over the close to 4 years in Samsung, I pushed around more than 10 standards, more than 10 IPs into the LTE advanced standards. Okay, so each IP I would say it's more than tens of millions of dollars. If you regard it as essential IP. That's the reason actually I got the individual gold medal in 2011 at Samsung. Right before that, I was a visiting researcher in Mitsubishi Electric Research Lab back in Boston. And it's in Cambridge, United States, not Cambridge, UK, and it's very close to Boston. So this is very close to the campus of MIT, and this is actually the 6th floor building, and I'm on the top floor. And in fact, actually, April 6th, I'm going to promote a little bit. April 6th, we're going to have a distinguished lecture, rather distinguished lecture. One of the speaker is actually Li Zhongzhen from MIT. He's a good friend of mine. How I met him? I met him here. Actually, it's a Chinese restaurant called Mulan. It's just right next to my place to work. I go there every day. I met him. I said, "Oh, are you Li Zhongzhen?" He said, "Yes." Okay, we're on the line. Make sense? So of course I know him before that, but we met actually a lot of time in Mulan. So I'm working in Mitsubishi Electric Research Lab. What I'm doing is mainly doing actually things related to IEEE 802.16m, which is another thing called Advanced Mobile WiMAX. Okay, that's actually later on they lose to the 3GPP LTE supporting candidates. Oh, they are still candidates, but it's in a niche market. So before that, I was working GE China Technology Center back in China. Okay, right after I graduated from Shanghai, so it's in Shanghai. All right. So that's actually my brief background, and hopefully give you more information about who am I and what kind of things, what kind of experience I have. And if you want to work in industry after you get your degree, you can come to talk to me, and with high chance, I know some people you are interested in those companies. Because as a standard engineer, you have to interface, you have to interact with, let's say, most of the companies in the field. Okay, so, all right, so this is an outline, and I'm going to talk, today will be focused on something called rateless coding-based cooperative communication, and I'm going to discuss what is rateless coding-based cooperative communication. I'm going to talk about one-dimensional network, two-dimensional network, two-dimensional random network, and then dynamic spectral access network, and the USRP prototype. Okay, these are the actually main outlines. I'm going to conclude the talk. By the way, actually, I think it's, feel free to interrupt me, right? Or I have to wait until Q&A.
It's up to you.
Okay, up to me? Okay. You guys decide, okay? So the big question, what is 5G? It's probably $1 million question. So maybe $1 billion question. What is 5G? I think Dr. Jeff Andrews says a famous paper, right? What will 5G be? That has lots of citation because the buzzword. And he was telling me in GlobalCon 16, we were having actually beer together. He said his original title for that paper is, "What will 5G be? Maybe." That's his original title, and later on he changed. Anyway, ITUR. What is actually? So we can say what is 5G, but the key thing is that 5G is not defined by us. It's not defined by any individual company. Does that make sense? There's actually an entity defining what is 5G. So the entity is called ITUR, which is the Radio Sector of International Telecommunication Union. Okay, they have their own definition, and that's actually they'll specify 5G in different types of metrics, such that IMT Advanced use 4G, IMT 2020 is 5G. So they are, according to their definition or their metric, is saying that 5G is not just trying to improve the data rate. Does that make sense? I mean, because if you think about 2G, 3G, 4G, and most of the time we talk about data rate, right? We're saying that kilobits to megabits to gigabits. Okay, those are the evolution. But they're saying 5G is more than that. They're going to, let's say, of course, peak data rates from 1 gig to 20 gig. We're also going to increase actually user experience data rates. Your latency is very important. Okay, I mean, we are going to reduce latency from 10 milliseconds to 1 millisecond. And by the way, is 1 millisecond good enough? You're saying no. That's good. We're going to have a job, right? We still have a job. You're always pushing the boundary. By the way, is 1 millisecond good enough? Yes, it's pretty fast. 1 millisecond. Think about it, right? So, but anyway, there are more to it. Okay, we are pushing the boundary. So I was talking to Charlie. He's a close friend of mine. He's a Samsung vice president. I mean, once I was telling him, I said, "Oh, really pushing to 1 millisecond. What else we can do?" And he said, No. 1 millisecond. You're talking about applications like actually autonomous cars and things like that, right? But there's a lot of applications beyond 1 millisecond. Basically, even require lower latency. I said, what kind of application? Medical applications. Okay, he was talking to some of the medical doctors. They were saying that no, 1 millisecond is not fast enough. If you think about surgery type of things, remote surgery. Anyway, so no matter how much you have, you're always pushing the boundary. Okay, and also you have actually connection density and a very dense network energy efficiency and things like that. Basically, this figure tells you 5G is trying to cover everything. Okay, and then in terms of application scenario, ITUR specifies 3 very important areas. One is called enhanced mobile broadband, another is called massive machine type of communication, and the third is called ultra reliable and ultra low latency communication. What is enhanced mobile broadband? Enhanced mobile broadband is nothing but just I want to get gigabits per second. I want to get 10 gigabits per second, even 100 gigabits per second. What kind of applications? Think about virtual reality, okay, augmented reality, these type of things. Okay, those are data-hungry applications which requires very, very high data rate. What kind of enabling technology associated with that? Massive MIMO, millimeter wave communication, things like that. Okay, FD MIMO if you are working for Samsung, right? 4-dimensional MIMO. All right, gigabits per second. And another area is machine type of communication. Okay, massive machine type of communication. So application scenario is related to something called smart city. Okay, so a lot of devices connected together. So for those applications, you don't need gigabits per second. However, you need a lot of connectivity. Does that make sense? So there are different features associated with that. I think Dr. Harper did a lot of work here, and we also have collaboration on this related to sensing. Okay, so we actually for the enhanced mobile broadband work with Samsung a lot on the FD MIMO, massive MIMO, if you know this prototyping of that. Ultra reliable, ultra low latency communication. So what is this? This is related to self-driving cars, autonomous cars, and for those type of applications, you don't need the data rate very high, and you don't have massive connectivity, but you need to be very reliable. You need to send it in a very, very short fashion. Does that make sense? There's a car, okay, in front of you. All right. So potential technologies are related to FD MIMO, massive MIMO. We touched on this a little bit. I think one of my students gave a presentation in the Wadi seminar, and on this FD massive MIMO. And by the way, actually, world's first actually demo test bed of FD MIMO was actually developed by Samsung, and one of my Hao is actually my former student is participating in that. And waveform design, you want to design different new waveforms, like OFDMA is the waveform used for 4G, and for 5G, and in future, we are going to use OFDMA, different waveforms, okay? And also new spectrum, we are going to have new spectrum. And when you talk about new spectrum, most people focus on something called a millimeter wave. Does that make sense? I mean, which is, normal, because I think 2015, US actually FCC have this spectrum, millimeter wave band. Oh, finally it's coming. No, still not coming. Okay, so they mainly focus on millimeter wave spectrum, and US becomes the world's first country to have actually designated spectrum for millimeter wave communication for broadband. However, there's another actual spectrum which is very, very important, which is 3.5 gigahertz. Okay, this is something we can utilize. All right, now let's look at, for new spectrum, there's something related to called dynamic spectrum access. So what is dynamic spectrum access? Have you heard about this term? Who knows? Who didn't hear about dynamic spectrum access? Raise your hand. Or I can skip these slides probably. Okay, I'm going to be brief. So for dynamic spectrum access, you have two kinds of users. The first is more like a low priority user. The other is high priority users, and they are going to access the spectrum simultaneously. Okay, so they'll have some interference agreement. So, All right, so there's actually two types of access technology. One is more like overlay, another is underlay. So overlay is saying that, the high priority and low priority user use, let's say, disjoint, the orthogonal spectrums. Okay, underlay meaning actually they are going to use the same spectrum. However, the low priority user is going to transmit power is limited. Okay, to guarantee the the quality of service of high priority user, so that meaning that the low priority user usually have limited coverage for short distance communication because they cannot blast the network. Does that make sense? Because you are low priority users. Okay, you're not high priority. So, okay. Cooperation among low priority users becomes critical. What does this mean? This means actually if you look at a source and destination, this is underlay network. And if there's no underlay, if I have my dedicated spectrum, I'm going to shout it to the destination. That's it. Okay? But if I cannot shout, and these are talking about the range. Okay? If I might transmit, I have to limit my transmission power so that I don't cause too much trouble to the high priority user. So my coverage area is relatively small, so I cannot reach my destination. So what I can do is that probably I'm going to do multi-hop routing. Okay, I have actually a set of nodes who's helping me and hop that message from the source to destination. Does that make sense to you? So because I cannot shout to him directly. Okay, so this is actually indeed a good way of doing things. However, so most of the work in this area focus on something called multi-hop routing. So this guy route to this guy, this guy route to this guy, this guy route to this guy, and there are plain routing associated with that. So let's look at actually some feature of this. So cooperative communication, meaning these nodes are collaboratively send one message through the network from the source to the destination. So that actually is something called cooperative communication. And in cooperative communication, so we are trying to take advantage of the broadcast nature of a wireless channel. What does this mean? This means even though, let's say, node 0 talks to node 1, okay, so even though, let's say, the route is 0, 1, 2, okay, I'm going to send the message from node 0 to node 2, okay, I'm route to node 1 first. So if I'm route to node 1 first, because of the broadcast nature of wireless channel, and then node 2 will receive something, right? Should not completely discard that. You're going to receive something. And then node 1, when node 1 forward things to node 2, then node 2 already received something in the first time slot. You can think about it. Okay? It's nothing, it's not actually useless because it's related to the message, so you can combine it. Okay? Those are actually the nature and the cooperative nature. Oh, it's interesting. When I want him to move, it's not. It's automatic. So that's actually by forming. What? Okay. By forming. All right. So somebody is controlling this computer other than me. Okay. So broadcast nature, and then for example, if you node 1, node 2, node 0, and node 1 both have the message. So you can form a virtual antenna array, okay, and then node 0 and node 1 can do distributed beamforming, okay, and then form that antenna, form the signal to node 2. That's actually the idea. Okay, in this way, you can improve the reliability, throughput, and the coverage of the communication. Also, strategy for cooperation, usually you have multi-hop transmission, okay? That means actually you can have this node 0, this is the source, this is the destination, and then each node just receive it and forward to the next destination. Okay, that's actually multi-hop transmission. Alternatively, you can form energy accumulation. What is energy accumulation is doing that, if you have this is the source, this is the destination, okay, the source can keep transmitting, okay, to both of them, so until actually the first decode, and then after the first decode, and these two can do actually distributed space-time code or maximum ratio combining at the receiver side. Okay, to receive actually whatever, to combine those received message together to have a better reception of the message. Okay, those are called energy accumulation. Okay, but the key thing about energy accumulation, if you are familiar with distributed space-time code and the maximum ratio combining, is that at the receiver side or at the transmitter side, you need to know the channel. Make sense? Otherwise, how you can distribute the beamform? And you need to actually do this in a very, let's say, careful way so that they will not have other issues. So other than this, there's another thing called rateless code. So what is rateless code? So the rateless code, the idea of rateless code is that I'm going to encode a given message and encode that into potential infinite number of encoded symbols. Okay? That's why it's rateless. For example, you have K symbols, okay? K source symbols. So these are the encoding procedure. Out of the day, you can have infinite number of encoded bits. And then what is the code rate? The code rate is k divided by infinity, right? Infinity number of encoded bits, that's 0. That's why it's called rateless. And then the nice thing is that, as long as you receive k or a little bit more than k symbols, you can decode. It doesn't matter which k. It doesn't matter which k, and as long as I receive k, it's decoded. So that's why the very, very first coding is called fountain code. Okay? Just like a digital fountain. So the fountain is, you think about it, it's a digital fountain is generating fountain, and then you have an empty basket. Okay? You can accumulate a basket of water, and then you can decode it. It doesn't matter when you accumulate it. You can accumulate now and then do something else and accumulate the rest. Does that make sense? You go to the fountain, you accumulate. So every bit is new in some sense. All right, there's actually examples related to this code. It's fountain code, raptor code, and those codes actually later on we have spinal codes, right? Polar rateless code, and those are the new codes in this family. And for many of you, it's kind of strange. It seems that not so many people know this too much, but those codes have been adopted in standards a lot. Okay, if you look at 3GPP LTE and DVB, and those actually standards adopt these codes because it's very, very robust and nice. You don't need channel state information. Does that make sense? You don't need to know the channel. To some extent. Okay, you don't need to know the accurate channel and just to send it. All right. So from math point of view, the rateless coding, if you equip the rateless coding at the physical layer, if you assume rateless coding is adopted, so basically you achieve something called mutual information accumulation or mutual information combining. Okay, what does this mean? It is actually automatic. So a receiver can collect mutual information from 2 or more independent transmitters. Think about it, digital fountain. Okay, if I have 2 nodes that are generating fountain, I have 2 fountains. Make sense? And as long as I accumulate from these 2, I can accumulate and a certain threshold, I can decode that packet. Make sense? So, and this can be achieved where the transmitter uses independent rateless code. As long as, let's say, you receive the message, a node receives the message, you use independent rateless encoding, and then send it over the air, and then at the receiver side, you can do a joint decoding based on the receive from the 2 transmitters. You can do a joint decoding. You can get. Okay. So let's compare it. Let's compare this approach. The math is more like a mutual information accumulation, and then the distributed beamforming, or the maximum ratio combining, which is energy accumulation. Right? We know maximum ratio combining is improved energy. Right? So at the receiver side, it improves the received SMR. Right? So if you look at actually, let's compare these 2 strategies to see which one is better or which one has more advantage. So let's look at actually simple case, the simplest case, where 2 nodes talking to 1 node. Okay? That's the simplest. Because if you remove this node, it becomes point to point. It's not network. And Dr. Yang is there, and she probably say it's not network. At least you need 3 nodes to be a network, right? This is what I learned. All right, so you want to compare this, and then let's look at the binary erasure channel. Okay, the simplest of all. So that's actually the first channel we will learn, right? From coding or information theory class. So this node to this node is binary erasure channel. This node to this node is binary erasure channel. So on average, the PE of the bits will be erased. Okay, so these 2 nodes. So all right, let's look at energy accumulation. You are going to send the same information, right? Same information across these two nodes, and then on average, how many bits will be erased? If these 2 nodes send the same information over this binary ratio channel, how many bits will be erased? Okay, sorry. I'm sorry, I should have a better remote. I don't know. So on average, the PE squared bits will be erased, right? The throughput will 1 minus P. What?
Maybe you can just unplug the...
Yeah, okay. All right, on average, the PE square portion of the bits will be erased, and then you are going to have a throughput of 1 minus PE squared. That's per transmission. That makes sense? Every time, because I send the same bits. Right? That's actually distributed beamforming. Distributed space-time code is essentially doing this. And if you are sending mutual information, basically you are generating 2 different fountains, right? So you are going to send actually independent bits in some sense. If this is the case, on average, the PE portion of the bits is erased on each of the channel, and then you are going to have, let's say, this is actually the throughput. 2 times. So which one is bigger? This one or this one? Which one is bigger? Done. Always or under some certain condition? Always, actually. You can show it. Always this one is bigger, except PE equals to 0. Oh, no. Except P equals to 1. Sorry. Does that make sense? Extremely low SNR. All right, so now let's look at actually, so this is actually showing you some of the comparison between energy efficiency. It's a very, very simple example, okay? So let's look at actually a simple communication problem. So now we understand, it seems that rateless coding is useful. Then let's look at if we are equipped with rateless coding, what kind of things we can do. Okay, is that problem tractable? What kind of problem we are going to encounter? So we're going to look at L nodes, okay? And this network, obviously L is greater or equal to 3. And then you have L nodes, and they each can transmit and receive, and then we assume orthogonal transmission to start with. There's no interference among those transmissions, and each node can conduct mutual information accumulation through rateless coding. Basically, each node is equipped with rateless code, transmit and receiver of rateless code, and then you assume constant transmit power spectral density. Okay, and then the constraint that you have a total system bandwidth, you have a total energy constraint, you have L nodes, right? I have a total energy constraint. Okay, and then among all those nodes, and my objective is that I want to achieve the minimum delay transmission from the source to the destination. Okay, for B bits, for example. So that sounds like clear network setup. Let's look at first a simple, very simple network. And this is not even a network. Sorry. It says source is the node 0 and destination is node 1. So what is the strategy? Nothing fancy, right? You have a decoding or routing order. It's an order of nodes that successfully decode a message. So there's nothing fancy, 0 and 1. There's no other choice. Source transmitting until destination receive. Okay? And the transmission strategy is that source transmitting until destination receive the size B bits of message. All right, then what is the delay? The delay is actually B divided by the rate between 0 and 1, and it is achieved as long as you provide me enough energy. Right? We have an energy constraint. If the energy does not actually is sufficient enough, I cannot achieve anything. Does that make sense? So this is actually very simple or even trivial network, if we call it a network. Then let's look at a simple but non-trivial network. At least it's a network now. We have 3 nodes. Okay, 0, 1, 2. There are 3 nodes network. 0 is the source, 2 is the destination, and the message size B, we have 2 message size B. I want to send it. We have total energy budget of ET, and I wanted to send, what is the minimum delay transmission strategy? Okay, that's a question. What is the minimum delay transmission strategy? What should I do? All right, remember we have mutual information accumulation, or that means we have rateless coding. There are 2 possible decoding order or routing, right? 0, 1. For 0, 2, that means actually I don't care about node 1. I just keep transmitting until destination receive. Okay, so there's one way of doing this. So this is exactly the same as what we discussed previously, right? Just to change 2 to 1, that's exactly. So another way is that 0, 1, 2, meaning actually node 0 keep transmitting until node 1 decodes. And then let's decide later. Okay, so you will keep transmitting until node 1 decode. The first is node 0 keep transmitting until node 2 decode, which is the destination decode. I don't care about node 1, whether decode or not. Make sense? These are the 2 decoding order possible routing strategies. So for 0, 2, there's nothing fancy. So you just keep transmitting the node to receive, and this is actually the energy. So as long as the energy is greater or equal to this, then you can fulfill this requirement. Make sense? Or clear? Kind of trivial, right? So, but on the other hand, for 0, 1, 2, that's actually a little bit non-trivial. So you keep transmitting until node 1 decodes. And when node 1 decodes, node 2 may already decode it. Does that make sense? Because you enforce node 1 to decode, so you will send to node 1. What if actually node 2 is even closer to node 1? I mean, we don't know, right? If that's the case, node 2 already decoded, it's not very interesting. Okay? And then there's another case where node 2 only receive partial information. Does that make sense? Just like you have a bucket. Okay, you accumulate half of the bucket, or let's say 1/3 of the bucket of the water. You need another 1/3 or half to fulfill the bucket. Okay, you still need something. And then what we need to do under this operation, they have 3 options. The first is that node 0 keep transmitting to node 2, or you have node 1 transmitting to node 2, or they both transmit to node 2. Okay, these 3 options, which is the best option? It's actually not clear. Depends on the energy constraint, depends on the power constraint, all those things. It's highly non-trivial. Okay, the optimal strategy depends on the rate of this and the total energy. For example, if I don't have energy constraint, let's say I relax this energy constraint, what is the optimal strategy? Both, right? If I reduce the energy constraint, then probably later on there will be only one node transmitting. Does that make sense? Good. All right, so let's look at this example. At least it's a network, right? It's a huge network. We have actually source and destination. We have 50 nodes, and then we're going to transmitting from node 0 to 49, nodes 49. And what is the optimal strategy? So they are altogether this number of decoding order or routes. And for each one, how to find the optimal scheduling and how to find the optimal resource allocation. Okay, that's actually the issue we encounter. Does that make sense? Even for the 3-node network, it seems not that obvious. And how about this network? What is the best way to do? Okay, and then the issue related to this, we're going to see this through the example, is that, if you assume each node can accumulate mutual information, can do rateless coding, then the routing itself is not memoryless. It's memory. Okay, because how much you accumulate depends on who's transmitting previously. Okay, for multi-hop routing, traditionally, you don't have this. You don't have this memory in the problem. All right, let's look at one-dimensional network. Again, we have a 1D topology. We have n+1 nodes equally spaced from 0 to d. Okay, this is green is the source. This is destination. All right, and then we have the distance between these equally spaced. That's why you have d total d divided by n. You have n+1 nodes. That's why you have n intervals. D divided by n is actually the internode space. All right, and then you assume free space propagation model. Okay, and then you assume each node have the same power spectral density. Okay, you have a system bandwidth of total of WT. Okay, so that is a total system bandwidth for the whole system, for the whole network. You are going to share. If 2 nodes are transmitting, they need to share. Okay, 3 nodes transmitting, they need to share. The objective is that I want to send B bits from the source to destination with a minimum delay. Okay, so all right. So there are 2 strategies. One strategy is multi-hop routing, decode and forward. Okay, each node just send it to the next node, which actually you plan that node, and then that node forwarded to the next node or whatever until it reaches the destination. Okay, that's multi-hop routing. You can use multi-hop routing strategies to find out what is the delay to transmit BBS across the network. Okay, usually you use Dijkstra algorithm to figure out what is the optimal, the shortest path or shortest delay. Make sense? Another way is that you can use rateless coding. Okay, you can use rateless coding based cooperation to transmit. So though when source node is transmitting, everybody is listening. Okay, and then the optimal strategy for this particular network. Do you know what is the optimum strategy? What is the optimal routing for the mutual? If you assume you have rateless coding based cooperation. For this, it's not clear because node 0 is sending. He should have a target, right? He should target for the next hop. Does that make sense? Actually, the target of that next hop depends on the power he has. Okay. But however, for rateless coding based approach, it's always next node. Okay? So source will keep transmitting until node 1 decode. After node 1 decode, node 1 should pick it over to transmitting. Why? Because for all the nodes after him, node 1 is always better than node 0. Does that make sense? So there's no point asking node 0 to keep transmitting as long as node 1 decode. If node 1 decode, he should pick it up saying, I'm transmitting, and node 2 decode saying, I'm picking up, I'm transmitting, until the routing problem is extremely clear or straightforward. There's no routing issue, or there's no actually what kind of route we need to specify here. That's why if you look at this, you do the delay for this one, you do the delay for this one, you want this much larger than this, right? If this is less than this, okay, done. No need to. Okay, the problem. So this is that tells you what is the cooperative gain, and you are going to see actually the cooperative gain is actually changing as the transmission power. Why? Because these actual discrete points are the optimal route for multi-hop routing change. Does that make sense? Like I said, for the first multi-hop routing, it depends on the P times WT, and if this is large, you want to shout to the destination directly. Okay, if this is small, you want to talk to the next neighbor. Okay, so this is multi-hop routing. However, for the rateless coding base, it never changed. So it's actually, you look at when this increase, actually the cooperative gain increase. So even with very, in this region, you can reach 1.64. You can analytically characterize this gain. All right, now let's look at the two-dimensional network. This is a line network, which is relatively easy. Let's look at two-dimensional network. Two-dimensional network in this type of network is also relatively easy to figure out the route, at least for rateless coding-based cooperation. Why? Because this node is sending, this node is destination, and as long as these two nodes, any of these nodes actually receive, they should pick up. Does that make sense? They should actually pick up. There's no problem in terms of which node I should route to or something like that, at least. We remember initially we were saying that there are two problems, right? Routing problem and resource allocation problem. For this, there's no routing problem. You can figure out the route, optimal route, very clearly. So you can do this, and then this tells you actually the cooperative gain in a sense. Okay, the same thing. You can characterize this. And the observation is that, if you look at this, you can see that if you look at 2D network, rateless coding-based cooperation can achieve higher gains compared with the 1D network. Okay? And we didn't do 3D network, and I'm expecting that it's even higher. Okay? Higher gains of that. And does that make sense? Or clear? All right, now let's look at something interesting. This is random network now, because previously we focused on structured network. 1D network, 2D grid network, all those are more like a structured network. You can easily find out what is the optimal route, right? Because node 0 transmitting, node 1 is always better than node 0. In any respect, we should ask him to pick up the transmission. However, if you have 2D random network, it's relatively difficult now. There are source and destination. Okay? We want to send, you are going to send minimize the delay. The objective is to minimize the delay, and the constraint is energy and bandwidth. Excuse me. And the problem is that who transmits, when, for how long, and how much bandwidth. So these are the two critical questions, right? The first question is that basically the route, right? What is the routing? And then for fixed routing, what is actually a resource allocation? Okay, which one should be transmitting for how long, and then who's going to pick it up, and who's going to share? Does that make sense? These are the two critical problems. And in fact, we decompose this problem into two subproblems. The first problem is that for fixed decoding order, for example, you give me a route. If you tell me a route already, okay, just like 1D network and 2D grid network, if you tell me a route, okay, I can formulate the problem. I can formulate the resource allocation problem as a linear program. Okay, I can solve that linear program. Okay, so this node is sending, and something like, if I assume a route already, then I'm going to characterize the resource allocation using linear program. And then the second problem is basically, if I look at the solution of the linear program, and then that solution may tell me something about the route, so that I can improve my route, so that I can get a better route. Does that make sense? So one is a routing problem, one is a resource allocation problem. We are thinking that, if you do resource allocation problem right, that will tell you something about the route problem. And that's actually what we are doing. Make sense? So, all right, let's look at actual decoding order. And then the decoding order route is the order which the nodes are able to come online as relays. Okay? So, and always starts with the source and finish with the destination. And then you don't need to include all nodes. Okay? You can have actually arbitrary route to start with. Always start with the source and end with the destination. Make sense? So, and then for this route, if you tell me any route, for example, I start with the source and end with destination, any route, I'm going to form a linear program on this. Once I form a linear program on this, and what kind of linear program I'm forming? And forming is actually, I'm talking about internode decoding delay, meaning actually the transmission time you can think about related to the transmission time of each node. So the internode decoding delay meaning actually this delta 1 meaning actually this is the source, this is the node 1 decode, and this is actually the time where actually node 1 decodes. The difference in terms of node 0 is always have the message, right? This is actually the inter-decoding time, and then the overall delay from the source to destination is nothing but the sum of this. Okay? Just let you know these are the actual parameters of the linear program. After you formulate this into the linear program, you are going to solve, okay, delta 1, delta 2, delta 3, up to delta L. Okay? That will give you optimal solution for that. And if you do that, okay, like I said, we decompose into two problems. The first problem is what is the optimal decoding and routing. And the second is that for fixed decoding and routing, what is the best resource allocation strategy? Okay? For fixed decoding order and routing, we can use LP to find the linear program to find the optimal resource allocation. And however, there's a massive number of orderings, and you are going to search. The key thing is that we need to search the space efficiently. Okay? We need to search the space in a very efficient way. All right. Let's look at actually potentially one answer of the linear program. Okay? So what if actually the linear program tells us that delta 3 equals to 0? Okay? The delta 3 equals to 0, meaning what? Meaning node 2 and node 3 decode simultaneously. Does that make sense? Because you have delta 2 is non-zero, meaning actually after node 1 decode, there's actually tone for node 2 to decode. And the delta 3 is 0, meaning actually when node 2 decode, node 3 already decode. Make sense? This is actually something. And what does this mean? This means actually we probably, when we do 0, 1, 2, 3, we enforce node 2 to decode earlier than node 3. Does that make sense? Because we are forwarding that message. You can think about type of forwarding in the quotation mark from node 1 to node 2. I don't consider about node 3. But when delta 3 equals to 0 tells me if I enforce that, I mean node 3 already decode. Probably we can swap the order of node 2 and 3. Does that make sense? If I swap the order of this, then the original linear programming solution immediately become a feasible solution of the new linear program. And if you run the optimization again, you are going to get an answer which is better. Does that make sense? One of the constraints becomes non-active. Okay? So old solution definitely is a feasible solution for the new order. However, if you run the linear program again, you are going to get better or stay the same. Does that make sense? So this is telling you, hey, from looking at the resource allocation outcome, I can clearly see what is a better route. Make sense? All right. If you swap nodes L1 and L destination, you can drop it. So basically, I don't need to force that to decode before the destination. Okay? All I care is where the destination received. So that's actually how we do this. So what you are going to do is that you are going to interplay between linear programming and the swap, do iteratively. You are going to, until the LP solution, the linear programming solution, satisfy all this delta are greater or equals to 0, or greater than 0. Okay? And then only necessary local. So by doing this, it's only necessary a local optimal. For small network, it's usually a global. Basically, what you show, I mean, for example, to characterize optimum resource allocation and routing for this type of network is almost NP hard. Okay? So, but on the other hand, we actually show by doing this, you can always reach very good solution. Most of the time, they are optimal in terms of small network. But large network is not clear because we cannot do exhaustive search. Okay? So the problem is that when you have multiple delta i's, how to swap, how to do that, and if you are going to, so again another if you have multiple delta i's, how to swap, how to change the order, that's an issue we are going to face, and then you have different ways to resolve this. Another way is that, I mean, what is a good decoding order or good route to start with? Okay, that's also, remember for those type of algorithms, it's always very heavily depends on the initial condition, the initial point we usually start from flooding. Flooding means actually we don't have energy constraint. Make sense? So we are talking about energy constraints. So we don't have energy constraints, so what is the best strategy? Okay, we use that as a starting point when then we back off the energy. Okay, we back off the energy, again, we get this. So this is actually our sample result, okay? Tells you what we do, and for this whole network, and this dotted line is actually the multi-hop routing. If you actually use Dijkstra algorithm to figure out what is actually a routing, multi-hop routing strategy. So node 0 will send to node 9, and node 9 will send to node 49. Okay, only 2 hop to the destination. But if you are actually using Rateless coding-based approach, then you are going to have this node 0 will transmit until node 16 decode, and node 16 decode will take it over, and then send until node 33 decode, etc. Okay, go on until actually node 49 decode. So this is actually how we do this, and then we look at actually the coding order, energy budget. I mean, when the energy budget is large, so you can start with actually flooding order, the flooding route, and then you can back off the energy a little bit. Okay, when you do the back off energy, you can get this trade-off between the energy and transmission delay. So at minimal energy cooperative route, you are going to say only one node transmitting. Okay, if you want to, so at this point, if you talk about minimal energy, I want to send through this network using minimal energy, then only one node is transmitting. Okay, this guy transmitting until this guy receives, this guy keep transmitting until this guy receives, etc. Okay, only one node transmitting. So you have actually 20.1. Oh, so the delay is changing from 13 to 21. Okay, so that's actually the improvement. Also use less energy. All right. So the main gain from this to this. Let's say if you compare this Rateless coding-based approach with this, there's actually the gain mainly come from 2 facts. One fact is that because of Rateless coding-based approach. Okay, I can tell you if you just use this route 0, 9, 49. if you just assume rateless coding is used, you're going to get a lot of gain already. Does that make sense? Because you're not waste any previous transmission. Okay? But if you can further improve your route, you can get another gain on top of that. All right, so these are just for random realization. Just for 50 nodes, we randomly distributed it. Okay, so what we do is that now we for actually 500 realizations. So we actually have 50 nodes in an area, and we do actually 500 topology, okay, realizations, and we run the algorithm for this 500, and then you get actually distribution, CDF of the delay of 2 algorithms. You can find actually, this is actually shortest path algorithm, this is actually centralized and distributed. We have also 2 distributed algorithms to do that. Okay, you'll find actually.
In the shortest path algorithm, when you use Dijkstra's algorithm, what weights do you give to each edge? Is it the distance directly, or is it some function of distance?
Distance. So it's actually related to the rate.
Okay.
Yeah. So you compute we assume free space propagation, so you actually look at the rate between these two. Yeah.
So do you think if we give some other weights, then we could actually push the CDF corresponding to the shortest path towards slightly more optimal ones?
Yes, you can always improve, but in terms of improve, in 100% increase or cut half of the delay, it's almost impossible. So that's why there's a huge gap. If let's say these two are very close, then probably you want to optimize the Dijkstra algorithm to get actually closer to this, but the gap is huge. So, and especially if you look at most of the things, we look at the topology, fixed topology, which is pretty easy to figure out what is optimal for multi-hopping. Okay, so we have introduced 2 distributed. If you look at the average delay, it's 12.5 seconds versus actually 25 or 21. It's almost the same now. Let's look at another network, which, as we mentioned, it's actually dynamic spatial access network. So if you look at dynamic spatial access network, it's even more involved. Now we have the so-called primary transmitter, primary receiver. Okay, one is primary transmitter, one is primary receiver, and then you have actually n secondary users, and the one source, one destination, the other potentially serve as relays. So objective is that I want to send B bits from the source to destination, and subject to the total energy constraint, total bandwidth constraint, and a new constraint which is called interference power constraint. Meaning that collectively the secondary user cannot create interference to the primary user larger than I of t. Okay, that's the threshold. You need to make sure your interference is less than that. Make sense? So it's going to be something interesting because you're going to see this is actually the algorithm it goes through. So this is a primary transmitter, primary receiver. So this is actually, if you use the non-cooperative way, this is actually how you do. This is actually the time and bandwidth product. Okay, think about it, because this is not one because of interference constraint. So sometimes they cannot use their full power; they have to reduce their power. Okay, so if you look at actually this source destination, so if you look at the rateless coding base, it's much more. Let's say you are going to have more nodes involved in this transmission, and if you compare the CDF again, so you're going to see huge difference. Okay, here from the CDF of the end-to-end delay. And what makes life interesting is that we can characterize cooperative gain for a very line network, simple line network with primary transmitter, primary receiver. And this result shows the analytical results and the simulatory results for this. And you're going to see that if you have a stringent, that's a requirement of I of S, meaning you are going to interference threshold. Okay, if your interference threshold is actually reduced, okay, interference threshold constraint is reduced. Is that more stringent or more relaxed? If the interference temperature is reduced, that is a more stringent requirement because you actually cannot tolerate more interference. Does that make sense? You force the secondary user to transmit with relatively low power because you cannot cause interference to be more than this number. Okay, if you push this in. So you're going to see the cooperative gain, or the gain is even larger as I of this interference threshold becomes smaller. Okay, so this is because this kind of advanced feature of rateless coding based approach can accumulate those information that is very helpful. Okay, in those so-called contested or congested environment from military perspective. Okay, all right. So, all right. Let's talk a little bit about USRP demo at AFRL. So what do you do is that I was talking to Dr. Brewer earlier today. any demo is kind of challenging. And actually, we have to go there to do the demo using the USRP we have. And what we do that we have 3 USRPs, we have 2 laptops, and I mean, one laptop is controlling 2 USRP, another laptop is controlling 1 USRP, and the potential we can have 3 laptops controlling 3 USRPs. Okay, so and then we have this is the carrier frequency and the sample rate and the slot duration and all those parameters. So we use Raptor K, okay, which is 25. So what do we do? These are actually the Lunar Radio implementation, and we implemented actually the 4 protocol stack from the fly to the application layer. And we do 2 actually. Also, this is a graphics user interface we implemented for the demo. And then basically you can see how they accumulate bits, let's say, mutual information and things like that. So the 2 demo, the first demo we are doing is that a multi-hop relay. So the first is actually, this is just a multi-hop. So this node is sent to this node until this node receive and then forward to destination. That's a multi-hop delay, a multi-hop relay. And then another actually we are using this rateless coding based cooperation is this. The source node send, and then they encode it into Raptor code and then send to the relay destination. And because the channel, we put into a line network, and because of channel, the destination relay can receive, and the destination only receive part of that. And then you re-encode it, and then first you need to acknowledge this one, and then you first re-encode it, and then you receive the rest. Okay, and then acknowledge. So here, everything we demoed here, everything we don't assume any channel state information. Okay, and then everything is under control, wireless control, and wireless max. There's no WAN or internet connections connect them to synchronization. We have to do the synchronization and synchronize to the GPS. And in fact, actually, in the Air Force lab, we cannot. We lost the GPS. We don't have GPS. So what we do that we use actually the clock generated by the computer, and then all the USRPs synchronized to the computer clock to get it synchronized. Because synchronization is a very big issue, very, very important. Without synchronization, nothing is there. All right, so finally you got this. Okay, you got this message. All right, hopefully I talk about rateless coding-based cooperative routing. It's shown to be an efficient way to improve network performance. And then mutual information accumulation can achieve more cooperative gain in 2D than 1D. And then MIA actually can achieve even better gains in dynamic spectral access network with tighter interference threshold constraint. This is something actually we are kind of, initially we were a little bit surprised because, anyway, this is showing actually advanced technology is good, really more beneficial in those environments. And then equipped with mutual information accumulation at physical layer, network design needs to be updated. In a sense, you cannot just rely on traditional method, and you need to, because of the memory, okay? The memory of this rateless coding. All right, thank you for your time.